It's gonna be at 7 p.m. in this room as usual. At that day at 8 a.m. we don't have a class at 8 a.m. What is included in exam 3 is all of chapter 7 and all of chapter 8. Okay? Assuming that we're gonna cover chapter 8 by Monday, by this upcoming Monday. If not, I'm gonna definitely let you know if we didn't manage to cover that. But I'm sure that we'll do by Monday. If you are registered with the Disability Services, you need to contact them ASAP, preferably today. If you have any conflict with exam 3, as usual, go to the registrar, figure out who's the instructor that should give you the makeup. If I'm the instructor that must give you the makeup, pass by my office as soon as possible so that we can find a time around it and you can do your makeup. Now our final exam is scheduled, as you can all of you see on your VSPER account, and it is the 12th of December, and it's going to be in this room, ISP 135, and nice enough it is at 4 p.m. because other classes they have their exam at 8 a.m. So we have it at 4 p.m. in case you have any conflict with this final exam. Again, from now, go to the registrar, figure out the instructor that should give you the makeup. And I need to know ASAP because I have to write 2 finals, which takes a lot of time. So I need to know ASAP. With that, we're going to keep going with chapter 8 and maybe with the VSPER model. So we talked on today is Friday, so we talked on Wednesday. Okay, on Wednesday we talked about VSPER theory, and we talked that we want to change any structure from Lewis structure, which is one-dimensional, to 3D, because this is how molecules exist. They exist in a 3D, not as we write them on the page or on my computer or anywhere. They have a 3D structure. And we talked about that we can do that by transferring the Lewis structure into a VSPER symbol. And we should learn that, for example, if the VSPER symbol is AX3, it's a trigonal bipyramidal. If it is AX2E2, that's a band. So you need to know these by heart. Okay? Now, what is A? I'm just going to remind you what is A. A is the central atom, represents the central atom. X is going to be the terminal atom surrounding the central atom. If you have a 3, you're going to put a 3. If you have 1, you're going to put AX. We don't usually write 1, but when you have nothing, that's a 1. If you have lone pair on the central atom, the most major mistake that usually students do is they think about the lone pairs on the terminal. Those we don't take them into account. We take only the lone pair on the central atom. If we have one, we're going to write it as E. We don't write 1. If we don't write the E in there, that means there are no lone pairs in there. So we stopped the last time at AX5, PF5. And I said that the Lewis structure of the hypervalent compound, that means the compound that have more than the octet rule there, have 10 electrons around it, and that takes place for elements from period 3 on. They can kind of exceed the octet rule to have 10 electrons, 12 electrons, and sometimes 8 electrons. We said that this is translated to AX5, and this looks like this, which is trigonal bipyramidal, and it is called the trigonal bipyramidal because clearly you have a triangle in the middle and 2 pyramids. If you look at it, this is the first pyramid, this is the second pyramid. This is why it is called trigonal bipyramidal. Now, if you look to the handout that I gave it to you on Wednesday, it says on the side the angles, and it is stated AX. And what I mean by AX, that means the angle between the axial and the axial bone is 180. If we look right there, it's linear. Between this and this is 180. And between this and this and this and this the equatorial. We call these the two axial, and we call these the equatorial, and we refer to them by EQ. The angle between this and this is 120. And this is why this is the most stable for AX5. So that's the AX5. Now we're going to go, we call it the trigonal bipyramidal. Now I'm going to go back to that table. Now for SF6, I'm going to insert again. So the Lewis structure, again, SF6 is one of the hypervalent. 6. Definitely to get to the Lewis structure, I'm doing it the fast way, but definitely you need to do it then the total number of valence electrons, and you connect it to the terminal 1, keeping in mind that sulfur is inferior to 3, so it can exceed the octet rule. So for this one, the VSPER is A, represents the central atom. I have 6 terminal atoms around it, and no lone pair residing on the central atom. And that's gonna end me up with the octahedral, which is, let's see the difference between the octahedral and the trigonal bipyramidal. So for the trigonal bipyramidal, for both of them I have, no, that's not it. The axial one, 2 axial, 2 on the axis up there. The difference is what is in the equatorial. So in the equatorial, for this one we have 4 atoms. In this one, we have only 3 atoms. So this is the difference between AX5, which is right here, and AX6, which is right here. Okay? So if it is AX6, it's going to look like this. Now, this is not the end, because if you look to your table, there is much more on there. And now we're going to work on the others that they are there. Now, so if we go back to the PF5, which is AX5, and we said that it is trigonal bipyramidal. Now, if I look to the Lewis structure of SF4, so it's going to be sulfur. And this is the Lewis structure. Definitely, I'm doing the Lewis structure really fast in here, but definitely for you guys, just the total number of valence electron. So this is the Lewis structure of SF4. So it's going to be AX4E. So this is what we call the molecular geometry. But it's coming from the lone pair geometry for this, which we talked about the last time, that the lone pair geometry is what is originating from. So if that E was an X, what would it be? This is what is the lone pair geometry. So that would be AX5. So it's mainly coming from the AX5, which is the trigonal pyramidal. Did everybody get why it is originating from AX5? If not, raise your hand so that I can repeat it. Okay, great. So it's coming from the AX5. Now the only thing that I'm going to remove one of the bonds and I would put a lone pair. Where would I put that lone pair? Remember that the lone pair take more space than the bond. Why you need a lone pair? Because you have a lone pair on the sulfur. Remember, the sulfur is one of those that exceed the octet rule, and in this case, it's exceeding the octet rule. So it's not 8 electrons. So all of what we're going to talk about are hypervalent from now on, are hypervalent compounds. That means the compound that's going to exceed the octet rule. So if you count the number of electrons, as she clearly found that it is more than 8, it's 10. Yes, it's going to be 10 because it's a hypervalent compound. And how you figure out that there are 2 lone pairs from the total number of valence electrons, you will find there are 2 more electrons on it. Now, there is a lone pair. Where I'm going to place the lone pair that's going to take more space? Definitely where it is far away from the others. And in the AX5, which is the trigonal bipyramidal, I'm going to put it on the equatorial. Why? Because the angle between this and any other is 120. Well, if I put it here, the angle between this and this is 90. So this is why I'm going to put it on the, okay, I'm going to put it on the equatorial, and what does that remind you with? Seesaw, very good. So this is why AX4E is a seesaw. Okay? So all what you need to know is do the VSPER, think what is it originating from, and then keep in mind that for the AX5 you're gonna place the lone pairs on the equatorial, all of them on the equatorial as we go. Now let's try the CLF3. So if we write the Lewis structure of CLF3, again, it's a hypervalent compound. It's going to be AX3E2, mainly again coming from AX5. So it's coming again from this trigonal bipyramidal in there. Now I have two lone pairs, so I'm going to place the lone pair again on the equatorial. So if I do so, I'm going to do the first one and the second one. What is this? T-shape, and this is why AX3E2 is a T-shape. Now, in the exam, I don't mind if you would like to get something, a model like this, not as big as this one. There are smaller models there. If you want to bring it to the class and take this and begin removing and placing the lone pairs, I really don't mind it, whether it is in the final or in exam 3. It's up to you if you'd like to do that. Okay, so that's the other one, which is the T-shape. And the T-shape is the molecular geometry, and the lone pair geometry is definitely the trigonal bipyramid. Now, I'm going to go to another slide, which have exactly the same, just because we don't have enough space in here, which I'm going to talk about the last one, which is XE xenon F2. And this is the Lewis structure of xenon F2. It's going to be AX2E3. Again, it's originating from AX5, 2 plus 3, that's AX5. So if the lone pairs were just X's, terminal atom is going to go back to AX5. It's again the trigonal bipyramidal. And now again, I'm going to place all the lone pairs on the equatorials. So if I do so, I'm going to get a linear shape. And definitely all of these shapes and things are listed on that table. But this linear is different than the AX2 that we talked about before. Why? Because now we have 3 lone pairs. Because we talked about AX2 for the case of CO2 or BeF2, where it was linear but there were no lone pairs in there. Okay? Now we're done from all those compounds or hypervalent compounds that's going to originate from AX5. Let's see how we're going to deal with the octahedral for those compounds that have the lone pair geometry being AX6 octahedral. And that's what we're going to do next. So again, we said that for SF6, we did it and it was AX6, which is this octahedral, which is 2 axial at 80, and we have 90 degrees here, 90 degrees, and the angle in this is 60 between each one and the other. So the angle in there is 60 between each one. Now let's go to the BRF5. The Lewis structure of that is going to be clearly 5 fluorines around it. So that's going to be here. And 1 lone pair. Again, BR is one of those elements beyond periodicity. So it's a hypervalent. So it's going to be AX5E. In other words, it is originating from AX6. Now, for the AX6, the way that I'm going to place the lone pair is different than that of the trigonal bipyramidal. In the trigonal bipyramidal, I put all of them on the equatorial. Why? Because the angle was 120 between each bond. In this case, the angle here is 60. So if I put the lone pair and it's going to take more space, it's not preferable to put it in here. It's rather preferred to be 90 degrees rather than 60 degrees between each other. So this is where, in this case, I'm going to put the lone pair on here, either on the upper axial or the lower axial. It doesn't matter. We're going to end up with the same thing. And this is what we're going to have as a structure. And this is called the square pyramidal. It's a square and a pyramid. Square pyramid. Okay. Now we're going to go to the last case that's we're going to have in there, which is xenon F4. AX4, E2 clearly coming from AX6. Again, it's octahedral. It's coming from this one in here. Now I'm going to place the lone pair on the axial because it's octahedral. The angle will be bigger than putting it on the axial. So this is the first lone pair. This is the second lone pair. What is this? Square. Here we go. Okay. So that's we call the square planar. And that's the last structure we're gonna see there. Square planar. So those are all the things that we're gonna see. Just one comment before we start eye clickers. About this, we're gonna do some eye clickers. That a double bond is considered the same as a single bond in VSPER. What does that mean? I mean, if I have, let's say, C double bond something, H, let's say I have this. Again, those double bonds is going to be considered, we're taking into consideration only the number of terminal atoms, not how many bonds. So this, let's say I'm doing the VSPER for this. The central atom is carbon, so I'm going to represent it by A. How many terminal atoms are connected to the central atom? 1, 2, 3. So it doesn't matter if I have a double bond or a triple bond in there, or a single bond. Okay? So it's going to be AX3. It has no lone pair. So AX3, I go back, and it is a trigonal planar. Okay? Get the idea? So if you have double or triple bond, that wouldn't reflect on the central atom. All what you have to look is the central atom, the number of terminal atoms. And now let's get started with some eye clickers. And I'm gonna stop each one of them at, let's start with 150, and then we'll count down less than that. So your first step is to write down the right Lewis structure. This is what happens in exams. Students look and they are, oh, this is gonna be AX3 or AX4, and they don't draw the Lewis structure. 50% is gonna be wrong. 50% is gonna be wrong. So draw the Lewis structure before you go any further.
What'd you say?
and I have 77% for C. C is the right. So first of all, carbon is the central atom, the two sulfur around it, the total number of valence electrons. Carbon belongs to group 4 electrons, plus sulfur belongs to group 6. That's a total of 16 electrons. I have 2 bonds, each corresponds to 2 electrons, so that's going to be 4 minus 4 electrons in bonding. So that's giving me a total of 12 electrons. I'm going to put them on 1, 2, 3, 4 on the terminal atoms. 6, 6. Then I looked at the carbon, it have only 4 electrons, and it means definitely the octet rule. So I'm going to borrow those 2 electrons and those 2 electrons, and I'm going to end up with this structure where each atom obeys the octet rule. Now, I have to go to the next step, which is VSPER, taking it from one-dimensional to 3D. This is the central atom, it's A, and if the terminal atoms is AX2, no lone pairs on the central atom, so that is linear. So in real life, the sulfur one gonna look like this. Definitely it's gonna have carbon here and then sulfur there, but it's gonna look linear. Okay, let's go to another example. Or another eye clicker. Let me just walk you through this. So what is the electron pair geometry and the molecular geometry of NO2 minus? Now, if you choose A, that means you're telling me that the electron pair geometry is trigonal planar and the molecular geometry is bent. If you choose B, that means you're telling me that the electron pair geometry is linear, the molecular geometry is linear. So, again, I'm going to stop it at 150. Okay, so I'm going to stick it right here and check what you think. Cool. And I have A at 54% and 39% for B. A is the right answer. So let's see. So the first step is to write the Lewis structure. Nitrogen gonna be the central atom that connected to the 2 oxygen. The total number of valence electron, nitrogen belongs to group 5 and the oxygen belongs to group 6. I have 2 oxygen in there and I have a minus. That means this whole polyanion gained 1 electron. So I'm gonna add that there and that's gonna be a total of 18 electrons. And I have 4 electrons in bonding. That's ending up with 14 electrons. Thus I'm gonna place them on the terminal, 6 for each hydrogen, then 2 electrons gonna reside, 1 lone pair gonna reside on the nitrogen. Yeah, this is not the octet rule for nitrogen, so I'm gonna borrow one of those there. So and definitely I need to put a minus for that to be wrong. Now my next step is translated to the VSPER symbol. So nitrogen is a central atom A, two terminal atoms, so it's AX2, and the lone pair on the nitrogen, so it's AX2E. It's originating, that means the electron pair theory is AX3, because if E wasn't a lone pair, it was a real terminal atom, I'm gonna end up with AX3, which is trigonal planar. So it's a trigonal planar. So it's a trigonal planar, and I'm gonna place a lone pair there. So it's AX3, I'm gonna place a lone pair there, so it's gonna look bent. So A is the right answer, trigonal planar and bent. So let's go to the next item here. Okay, we're gonna stop it at 150 and check what we did. And I have 76% for B. That's a very good percentage. So B is the right answer. So again, Lewis structure, sulfur is a central atom with 3 oxygen terminals. The total number of valence electrons, I have 3 oxygens, group 6, sulfur also group 6, and I have 2 minus, that means this whole polyanion gain 2 electrons, so I'm going to put that into consideration. I'm going to end up with 26 electrons minus 6 electrons in bonding. I'm going to end up with 20 electrons. It's going to be 6 electrons in each nitrogen, on each oxygen. I have 3 oxygens, that's total of 18 electrons. So I'm left with 2 electrons on the sulfur, and I wouldn't forget that it's a bracket 2 minus. Now I have to go from the Lewis structure from the 1D to 3D. The central atom is sulfur A. It has 3 terminal atoms and a lone pair, so it's AX3E. It's coming from AX4, which is this tetrahedral, and I have to place a lone pair. If I do so, it's gonna look like a trigonal pyramid. So B is the right answer for this. Okay, let's do some more of this. We're gonna keep practicing until we get a very high percentage for the right answer. What is the electron pair geometry and the molecular geometry of C2H2? gonna stop it at 150. Check what you think then. Okay. So I have 58% for B is the right answer. So first of all, again, the carbon gonna be the central atom because there is no way that hydrogen will be a central atom. Hydrogen are always or is always a terminal atom. So definitely I have to connect the carbon to the carbon and the hydrogens. Usually always make it symmetrical. I know that you have the choice to put it here, but almost always try to draw it symmetrical when you're doing kind of the basic connections. Now the end total, I have two carbons, they belongs to group 4, that's 8 electrons plus 2, that's total of 10 electrons. I have 1, 2, 3 bonds, 3 minus, that means 6 electrons bonding, and I'm left with 2 electrons that I have to reside it on one of those. There is something wrong with it. 2, 4, 2, that's 8, 9, 10.
10 minus 6 is 4.
Excuse me? 4 electrons? Yes, 4 electrons. Okay, now it's wrong. Okay, so now I'm looking to this carbon to have 6 electrons. So most probably if I put those in pairing and those in, every carbon would have enough. So that I'm gonna make 3 triple bonds, and I know for sure that carbon, nitrogen, phosphorus, oxygen, and sulfur, those are the ones that can make a triple bond. And this is clear on the Lewis sheet that I gave you, the Lewis kind of explanation. So that's and me to carbon, triple bond carbon. So maybe it's hard to tell what's the central atom in here, but looking to the, I'm gonna take one carbon of those and think about it as VSPER. So this is AX2, because this is the central, and it have 2 terminal atoms, and this one gonna have AX2. So the whole molecule gonna be linear. The whole molecule with the 2 carbons and the hydrogens around it, it's gonna be linear as an electron pair and as a molecular geometry. Now we're going to talk later on, because C2H2 is hydrocarbons, and hydrocarbons are what you're going to study in orgo later on, which are those compounds that have carbon and hydrogen. We're going to kind of spend some time on next Wednesday on how to draw organic compounds like these, how to draw the Lewis structure of those compounds. Okay, let's do one more. Okay. So I'm going to stop it at 150 and check what you think. I have 59% for B. B is the right answer. Again, we have CL, the central, and the 5 of them. So CL gonna be the central, and you should keep in mind that CL is period 3 and beyond, so it's gonna have, it is a hypervalent, it can be a hypervalent compound that exceeds the octet rule. The N total, I have 6 atoms which belongs to group 7, that's total of 42 electrons. I have 1, 2, 3, 4, 5 bonds minus 10 electrons in bonding. That's ending me up with 32 electrons. On each fluorine, 6 electrons, 6 times 5, that's 30 electrons. So I'm left with 2 electrons that's gonna reside in here. That means VSPER-wise it is AX5E, that means it's coming from the AX6, which is the octahedral. And I have a lone pair. Usually we place the lone pair on an octahedral on the axial position, which end me up with the square pyramid. So the structure of this is a square pyramid. So B is the right answer. Okay. Let's do one more. So again, I'm going to stop it at 150. And check what you think about it. Very good. C is the right answer. Again, I'm going to put xenon as a central atom. The N total, xenon belongs to group 8, 4 times 7, because I have 4 fluorine, they belongs to group 7. Total of 36 electrons minus 8 electrons in bonding. And whatever left is 28 electrons. I have 4 fluorines, each gonna accommodate 6 electrons, that's 28, that's 24. I'm left with 4 more electrons. According to the VSPER, it is AX4E2, mainly coming from the AX6 VSPER, which is the octahedral. For the octahedral, we place the lone pairs on the axial rather than the equatorial. So I'm gonna put on the axial lone pair and on the axial lone pair. I'm gonna end up with this very nice shape, the square planet. Okay, let's do some more. Till you go out of here and you know how to do any of these. Okay, so I'm gonna stop it right here and check what you think. And I have 77% for A. Very good. A is the right answer. So I is the central atom, ER, 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 and the total number of valence electrons. The 4 atoms belongs to group 7, so 4 times 7 electrons, that's a 28 electrons. 3 bonds minus 6 electrons in bonding. I'm gonna end up with 22 electrons. So each we are gonna accommodate 6 electrons, 6 times 3, that's 18. So I'm left with 4 electrons as a 2 lone pairs on the iodine. So it's A, iodine is a central atom, AX3, 2 lone pairs, E2. It's coming from the AX5. Sorry, let me rewrite that. AX5. So which is the trigonal bipyramidal. Where I'm gonna place the lone pairs in the trigonal bipyramidal? Axial or equatorial? In the octahedral, we're placing them axial. Where are we gonna place it in the trigonal bipyramidal? Axial or equatorial? Everybody yell it out. Equatorial. Where are we gonna place it for the AX5? Equatorial. So we're gonna put 1, 2 on the equatorial. Okay, and we're gonna end up with T shape. This is why A is the right answer. Okay? And lastly, we can have the last eye clicker for today. Use the following Lewis structure to determine the geometry of the following atoms. So the way that we're gonna handle this is carbon 1, C2, C3. So I numbered the carbon in this Lewis structure. So I already drew the Lewis structure for you. Okay? Then you have those atoms numbered. So if you choose A, you're telling me that carbon number 1 is tetrahedral, carbon number 2 is trigonal bipyramidal, those 3, 4 are trigonal planar, and so on, so on. If you choose B, you're telling me that carbon 1 is tetrahedral, 2 trigonal planar, 3, 4 linear, and so on. Okay, so start, and I'm gonna give you 150. You need more time than 150. So I'm gonna give you 220. I'll stop it at 2 minutes 20, so that you will be able to look at each atom and determine what it is.
3 and 4 will be linear because the carbons are intricately next to each other. There's no valence electrons in the room.
Sorry, so wouldn't it be here?
No.
So the trigonometry. This is the trigonometry.
No, this is linear.
So wouldn't it be linear?
Oh, it wouldn't.
What?
Okay, hold on. So I'm gonna start solving it as you're answering. So first for carbon number 1, carbon is a central atom. It is surrounded by 1, 2, 3, and all of this is going to be considered one terminal atom. So it's AX4. So clearly it is tetrahedral. For carbon number 2, okay, you're going to see something like this like that. It's up to you. If you want to leave, leave. In the second one, it is A, carbon is a central atom. Then I have 1, 2, 3 terminal atoms, so that's trigonal planet. So this is carbon 3 and carbon 4. It's asked to take it as 1, and clearly it is AX2 because this is going to be considered now the central atom, and you have 2 terminals, so it is AX2, it's linear. Again for 5, carbon is a central atom, and you have 4 terminal atoms, so it is tetrahedral. For 6, which is an oxygen, A is a central atom, 2 terminals atom, AX2, and 2 lone pairs in there, so it is AX2E2. So it's coming from the tetrahedral, yet we're putting the lone pairs there, and it is a bed, which makes B is the right answer. Okay? Enjoy your weekend, and I'll see you Monday.